Okay, I think I am recording now. So, all right, the next one we have you're seeing it. Which experimental feature of the MALDI MS technique um, allows the separation of ions formed after the adduction of tissue molecules? Um, so
Yeah.
I'll just go over like some of the passage. I mean, it's really not that much, but so okay, MALDI is just something that, all right, basically the first paragraph doesn't say anything. We basically just,
I love how you just don't care about the passages. Like we
yeah,
haven't even read the passage yet, and we already answered two questions.
yeah. It's like, all right, cool story, bro. Like now, you know, all I need to see is like, the schematic of the ion, figure one right there.
Mm-hmm.
So basically we have some plate called the MALDI plate, and there's tissue, and there's DHB, and that electric field line indicates that it's going upwards.
The electric field. Okay, yeah, yeah.
And if you remember, electric field lines go from positive to negative.
Yes.
So yeah, something. So that's why when the DHB attacks the whatever tissue, it becomes positively charged, and it's attracted to the top, the MS detector, because that's gonna be more like negatively charged.
So when DHB attacks the tissue, it becomes positively charged,
Mm-hmm.
um,
Yeah.
and then it kind of pulls the tissue particles into the MS detector.
Mm-hmm.
Okay, why the tissue particles negative?
Oh, why is the tissue particle negative?
Or like why is it that they're able to be
I think
pulled? Or like is there somewhere that I need to look for it
oh
to
yeah,
like tell me? Or
sorry. That's the electromagnetic radiation part,
okay.
like that arrow. You see it?
Mm-hmm.
Okay, that causes it to ionize.
Okay.
Um, yeah. So basically, the entire this entire system basically. I guess I shouldn't have just. So all right, whatever. MALDI, I'll just say the first paragraph is a soft ionization technique used in conjunction with mass spectrometry to analyze protein fragments, and peptides. I don't really think that helps that much, but maybe I am missing something. But basically, I just look at the figure, and I basically see, and then right above the figure, it says the radiation ionizes the DHB in the setup shown.
Oh, okay. Yeah.
Yeah. So, um, yeah, and then underneath it, it says the biomolecules M are adducted by free protons from DHB, and form this positive ion and positive two ions, and yeah, they leave the plate due to that electric field, and yeah, once they reach it, I guess they measure like how long it takes um to figure out its mass charge ratio. So
Okay.
so so yeah, basically what they're doing is they're just that's how they're going to um separate these biomolecules, aka the tissue.
Mm-hmm.
So the question's asking which experimental feature of this allows the separation of ions formed after the adduction of tissue molecules.
Which experimental feature of the BMS technique allows the separation of ions?
Uh-huh. So let's go, choice by choice, right?
Mm-hmm.
Does distance traveled by ions depend on the ion charge? If so that Could
So
be.
before that, sorry to interrupt you. Before that, I'm not even sure if I can understand the question. So it's asking what feature of this whole technique is allowing the tissue particles to separate in ions and kind of like attach to the DHB molecules. Is that the question?
It's just basically asking, yeah, why does this work?
Okay. All right.
Yeah. So okay. Now, what do you so all right, let's just go choice by choice. Distance
Mm-hmm.
traveled by the ions depends on the ion charge. What do you think about that?
No, it doesn't depend. It's always going to be the same. No?
Yeah. Why is that? Like, why wouldn't
Because
just stay there?
why wouldn't what? I'm sorry, you were cutting off.
Oh yeah, why wouldn't this guy just stay there?
Which sorry, I was not looking at the Zoom. I was looking at the
Oh, sorry.
question. Why would the black particles stay like in the multiplate?
Just stay in this place in between the multiplate and the MS detector.
Oh. I don't know.
Because it wouldn't, because there's nothing there, right? Because okay, what they're trying to do with that question is they're trying to make you think of, like, let's say if it was a gel.
Mm-hmm.
Because a gel, the distance traveled by whatever thing, right, depends on, its size and things like that. So they're trying to make you think that route. But it works in a gel because it's a gel. it has, it's going through something, so it has support. But all we have is there's nothing here. So all we just have is basically, like, a positively charged end here and a negatively charged end there. So everything is going to reach the top there.
Okay.
So,
But then the answer choice said the distance traveled by ions depends on the ion charge.
yeah.
So what I was trying to say is like that was not the right answer because it doesn't really depend on the charge. So I thought about like the positive or just Coulomb's law in general. So like if the distance is going to be the same, just negative or positive, even if the charge changes the charge. Like it's going to be the same magnitude.
Yeah, it'll be the same distance just because the distance between the MS detector and the MALDI plate is just one distance.
So all of the particles are going to get to the MS detector.
Yeah. Yeah. Because there's nothing that's going to keep it, hovering. If that was the case, we'd have like flying cars and stuff.
Mm-hmm.
So okay. So A isn't going to be it.
Mm-hmm.
What do you think about velocity of ions?
I don't understand that answer, Joyce.
Okay.
I was trying to read it before you asked me, and I was like, oh, I don't know what they're meaning there.
Okay. So I will say that, the important part to read here is what's under the figure 1.
Mm-hmm.
Because that's where, they're basically explaining it. They're saying that the ions leave the MALDI plate, right? And, they travel to the MS detector. So we know that they all get there.
Mm-hmm.
Then it says the velocity of the ions is inversely proportional to their mass charge ratio. So
it's pretty much B.
pretty much, right? It is.
I mean, they pretty much said it there. I just I didn't read that part, but the velocity of the ions is inversely proportional to their mass to charge ratio. Okay.
Yep.
Time of travel. How about C?
Time of travel is inversely proportional to the mass to charge ratio. So okay, so velocity and time are inversely proportional to one another.
Yes.
So
If I am basing myself of that statement on the passage, then it's actually, they actually have to be, time has to be directly proportional to the ion mass.
yeah.
Okay, let me see. So
yeah, I would write down like, oh wait, what is this? One of our services is down. Jesus. Okay, so
what does that mean?
I don't know. I'll go back. Let's try this again. All right. So okay. Geez. One of our services is down. I can't believe this. But okay, I was just going to say that if the velocity is inversely proportional to the mass charge ratio and time is inversely proportional to velocity, that means that time is proportional to the mass to charge ratio.
Yeah.
AKA, higher the mass, slower the velocity, which means it's going to take, and slower the velocity means it's going to take more time to get there.
Because the mass to charge ratio is higher.
Well, just like, yeah, pretty much, but yeah, it's like if something's heavier, it's going to be moving slower, so its velocity will be lower.
Mm-hmm.
And if its speed is lower, if it's slower, it's going to take longer to get to where it wants to go.
Okay.
So C is incorrect. If it said proportional, it would be correct.
Okay. Got it.
And then if we look, okay. So yeah, then it says electric field between the MALDI plate and the MS analyzer is uniform. So you're going to see sometimes some true statements, but you have to see if it answers your question.
Mm-hmm. So, I mean, it's a true statement because in the passage they're saying that the detector, or it travels a distance of 0.5 meters to the MS detector within the uniform electric field. But this is not the fact, or like this is not making it, or like this electric field is not what's causing the separation of the ions.
Yep. Yeah, and you notice how it says velocity of ion depends on the ion mass charge ratio? It doesn't say, because again, they want to trick you, because we see it saying in the passage, velocity is inversely proportional, right? And
Right.
then C says inversely proportional, but it doesn't say velocity. Whereas B says velocity, but it doesn't say inversely proportional. It says depends, which it does. It's just not being as specific because they want, you to be like
Pick C. Do they want you to pick C? Is that what they want?
Yeah, things like that. I mean, like if they want you to pick C because they want you to focus on the inversely proportional part in the passage, they want you to pick A because they want you to think of it as a gel. And I don't know why they would want you to pick D.
Okay. All right.
Okay, so the next one. So now we're gonna do some like a calculation kind of thing.
Okay.
So
I'm just very concerned at this point that we haven't really touched any content. So like this makes me.
You've done more than enough content.
Oh my gosh, like this makes me really worried, like in the good sense, because we really haven't.
Yeah.
I mean, like I try to ask you about like certain formulas and stuff, and you're like, you don't need it. Like here's what you need to.
Yeah, and you know, see how with that quinone question and stuff, I was saying like, yeah, I don't know what it looks like, but we can deduce that. We can make like an educated guess that lets us like, you know, answer like the question. Like here, like this entire thing we answered without I mean, I verified it afterwards here.
Right. But see, that's the thing. You trust your intuition, which is, or like your background knowledge, even if you didn't know what a quinone was, or if you didn't know exactly what a carboxylation and hydroxylation was at first. But like if I try to go to that process, I'll most likely pick the opposite answer because I'm like, no, obviously I need to know something to answer this question. It can't be just that I answer without anything else, you know?
You said carboxylation from the start, and on the actual test, you're not going to have any choice. It's just going to be what you have. It's just going to, you know, you're not going to have any choice but to have to use what you know at that moment in time.
Right.
So,
okay.
like in that PowerPoint that I made about like my tutoring, I said like one of the main things that I try to teach is tolerance of uncertainty. So if you don't know, it's okay.
Okay.
There's a way to figure it out. So, so yeah.
All right. So we're in question 4, right?
Yes. So this one basically is just, you know, they're asking us. So we're gonna look at, you know, table 1, right? Okay. So you see like basically how, you know, I'm going at questions first and then I'm, you know, going to where I need to go. Okay. So they're asking which laser is suitable for this technique after its frequency is doubled. So, you know, I guess you should know. So I'll tell you, you know, some types of content things you should know. It's not like really that like, you know, big, but you know, like how energy is proportional to frequency.
Yeah.
Okay, how about this? So is the frequency of UV light lower or shorter, or rather higher than I don't know, like visible light?
That I guess that's something that you have, or like, are you asking me based on the chart? No.
Oh, just
it
from
will be so. So
about.
yeah, frequency is directly proportional to energy. So higher frequency.
Okay, good. So you all right, good. So you know it. I was just gonna, you know, say something if you didn't know it.
Okay.
Because yeah, basically yeah. So UV light will have more energy and it would have a higher frequency, and that's how it's, you know, it's going to be damaging to us basically. But anyway, so you know that, right? So if we double the frequency, right, we're going to double the energy of that, like whatever wave, right? Okay. So what do they give us? They give us wavelength, and they give us power, and they give us whatever pulse duration, right? Now tell me about power.
So they give us wavelength, power, and what else these? Oh, pulse duration. Got it. Okay.
So what can you tell me about power?
So power is the amount of energy per unit of time.
Perfect.
So higher power will be higher amount of energy per second or per whatever it is, right?
Higher power will be a higher rate of energy like transfer, right? So you know they basically give us everything, you know, we need, like so how do you go from power to just energy? What would you multiply it by?
By the time.
Good. So they give us power, they give us pulse duration, aka time. So that's how we're gonna find energy, right?
Yeah. Oh my gosh. This is.
And then, you know, okay, and then with wavelength,
So
yeah,
shorter wavelength, higher frequency.
yeah, good. And all right. So yeah, you know everything. You know all the content. So
No, I don't. Oh my God, this is like,
yeah.
this is basic stuff.
So let's see. So basically, whatever. So they're out there. So let's say we double the frequency, right? Then we're gonna double the whatever energy. Um, but they're asking us basically. So all right, the table 1 shows us like the things that they use in the Maldi technique, and that is going to come into play here. Now, so okay, the power and pulse duration things, we don't really need to know that now, but okay, so if you double the frequency, right, you half the wavelength, right?
Yeah.
Okay, and then vice versa. Yeah, and so they're in the table. Basically, they're giving us the types, like the specific types, like that you need in order to use it for Maldi.
Mm-hmm.
And so we're going to have to see something where the frequency is doubled, but it would result in a wavelength that's either 266 or 325.
That is, oh, or a, I guess not, okay, I know what you're saying. That it's a multiple of those two numbers.
Yeah, so basically if we if we double the frequency, right, we're going to basically have something that is if we double the like frequency, how do we
Is
get
it D?
D 266 times 2? Yeah, because the other one would be like 750, I guess.
Yeah, the other one will be 750 and it's not there unless it's 266 times 3. Oh no, but we're doubling it only, so it has to be times 2.
Yep. Yeah, we're just doubling it. So yeah, I would look at this and separate by power. So 1.2, 1.2. Wait, I don't even see anything that's 1.2. But there's 1.5 and 1.5, so I would cross out A and B right away. And then I would just see basically like if we double the frequency, what happens to the wavelength in order to make it. So basically at what so which one of these lasers, A, B, or C, or D, would that has double the frequency would result in something with a wavelength of 266 for C and D. So
which laser is suitable for the molecule after its frequency is doubled? The frequency of what is being doubled? Of the laser?
yeah, the lasers in the choices. So they're saying that so for instance, for D choice laser D, it's a laser that has a wavelength of 532 nanometers, right? Now, when you double the frequency, you cut that wavelength in half, and you get 266 nanometers, and that is, the type of laser that works for this MALDI technique.
Okay. But my question is, it says here, which laser is suitable for the MALDI technique after its frequency is doubled? So after what frequency? The frequency of the laser is doubled. So let's
frequency,
say like the right choice is laser D, right? So I have laser D, which has a wavelength of 532 nanometers and a power of 1.5. If I double the frequency of that laser D, then the wavelength is going to go down to 266, and I'll be able to use it in the MALDI technique.
yeah.
Okay.
Yeah. So I like basically that word suitable is what they're saying. So like it's almost like, let's say you're in charge of this MALDI technique thing at a lab, and some guy is like, all right, I got laser A, I got laser B, I got laser C, I got laser D. All right. Which one do you want? And you're like, okay, well, MALDI only works with, this type of wavelength and power and this other type of wavelength and power, right? So you're going to choose something that will work for the MALDI technique, basically something that would give you that wavelength of 266, power of 1.5, and choice D is the only one that does that.
Okay.
So, yeah. Does that make sense?
Yeah. Unfortunately, it does make sense. What can I tell you?
Okay. All right. The next one, it says, according to the data in table 1, what is one of the values of, all right, so this is where we basically use, we're going to multiply power by pulse duration to get our answer. And
into the data in table 1 was okay.
yeah. And by the way, so power and pulse duration, they're in milli, like, which is basically times 10 to the negative 3. And if you multiply two things that have the same powers, you add
it's gonna go to the negative 6.
Exactly. So that's why the choices that you see are in micro.
Oh my god.
Mm-hmm.
Yeah.
Okay, so basically, so we basically have two options: 1.5 times 5 or 2.2 times 2. 2.2 times 2 is 4.4.
Something. Yeah.
I don't really see that. 1.5 times 5.
That's like 3, 4.5. I guess I can just do the multiplication, no?
Yeah, there's different ways you could do it.
How would you do it?
Oh, I guess I would just do whatever. I guess I would do 3.3 over 2 times 5 is 15 over 2, which is 7.5.
Are you writing something down? I don't know if you're. Oh, okay. So it would be 3 over 2.
Yeah, just because you know how I like to use fractions.
Yeah.
So 1.5 is 3 over 2.
By 5, right?
Mm-hmm. And then 3 times 5 is 15, and then it's 15 over 2.
So it's 7.5. Oh my god, it's so easy with fractions.
Yeah, see? Yep.
It is C. Oh wow.
Yep. Okay, next one, protein fingerprinting. So, I'm going to go to where they talk about it. It seems like it's the last sentence of the entire passage. It's saying they can okay, so proteins can be fingerprinted using MALDI if they're subjected to proteolytic cleavage before analysis.
Wait, I don't know what time we started because I don't know if like you're keeping track of the time. I don't want to.
Oh,
I don't remember at what time we started.
Yeah, so basically, let's see, basically like 3, because from 2 it was just technical difficulties, and yeah, we can go like as long as you want like to go. Like, what do you?
I'll just do like the entire afternoon because like this is pretty entertaining at this point. I guess we'll do the 2 hours.
Okay, all right, we'll do that. So okay, they're talking about fingerprinting, right? According question 6? Okay. So, so then I would go to the last sentence of the paragraph. Of the passage. And it says proteins can be fingerprinted using MALDI if they're subjected to proteolytic cleavage before analysis. So they're asking what reaction occurs to prepare it. So basically they're asking which of these is proteolytic cleavage. So think of,
I'm thinking.
okay, think of the lytic part of proteolytic.
So I don't exactly know what it means by proteolytic, but I know you're breaking something, and the only thing I can know is that whenever you add water into a molecule, you're pretty much
Okay. Everything you said is correct. And
join two molecules together, you get a molecule of water. But whenever you break water to add it into a molecule, you end up with two different products.
Yeah. So I'm going to ask you like 4 things. So how did you know it was breaking it apart?
Because lytic means to break.
Okay. What is proteo? What does it sound like?
Can we say like from protein or no?
That's exactly what it is.
Okay.
And then also cleavage.
Right. Yes. Of course, cleavage. That's
Okay.
true.
And now oxidation and reduction, right? They go back and forth. Remember with that first question, they're not adding something, they're not removing anything, right?
Right.
So A and B are out.
And also, hold on, give me a second because
Yeah.
Can you hear me?
Yeah, I can hear you better actually.
Oh.
Yeah.
Hold on, give me 1 second.
Sure.
Can you hear me?
Hmm? Yeah.
Yeah, okay. Guys, that my earphones they died, so I guess I have to change it to my computer. So I guess I missed the last part you said, but about oxidation and reduction.
Oh yeah. So remember when we did that first question and we basically determined that redox, that's why it's called redox. It doesn't add anything really or remove anything really. It like like besides like maybe an oxygen, maybe like whatever, hydrogen respectively, but it can, go back and forth. That's why, it's redox. And isomerization literally doesn't really change it either. It changes like maybe a location of something. But
yeah,
yes, hydrolysis. And the last thing I was going to say was when you build a bond like through polymerization, it's dehydration synthesis. And that means water is given off. And
right.
the reverse must be through an addition of water. So that is hydrolysis. But you could have figured that out. Like you would have gotten this right because you see lytic and you see lysis.
No, but that's what I said when you asked me why hydrolysis, because I know that every time you're trying to break something, it's because you're adding, first of all, or I think about hydrolysis as like you are breaking a hydro, which is like you're breaking a water molecule to add it into something so that it breaks apart. And then hydration is when you actually join something and as a byproduct, you get the water. Is that correct?
The last part is dehydration.
Oh, dehydration, sorry. Dehydration, yeah. So you're obtaining a water molecule as a byproduct of joining those two molecules into a bigger, or like two monomers into a polymer, I guess. And then hydrolysis will be you're breaking a water molecule to break a bigger molecule.
Yeah. Basically, if you can. Well, basically, if this thing,
Are you writing something? I don't know if you're writing something. Oh.
Yeah, I'm gonna try to. But I think I have it written down for something with maybe polymerization. Oh, here we go. So check this out. So basically, yeah, all polymerization is dehydration synthesis, also known as condensation. And this is like how I see it. So see how this this is OH and this is H, and that makes H2O.
Yeah.
So that leaves, and then this O attaches to that this carbon over here. So that's dehydration synthesis, like, you know, if you want to know like kind of like how that works. I wonder if I talk about breaking the bonds, but maybe here, no. All right. But yeah, you got the right idea.
Okay. Yeah, no, I don't see anything there about breaking.
Okay. All right. We can move on then.
Okay. So 7. Okay, this is a different passage.
Mm-hmm. All right, whatever. Okay, so let's see.
I guess we're not gonna read it.
Well, you know what? All right, I'll read it just so it can make sense. So let's see. So we have PAC is a technique used to determine the bond dissociation enthalpy of solute molecules. It's based on the photoacoustic effect in which matter emits sounds after it has absorbed light. The schematic is shown in figure 1. So we basically have, a pulse laser, and it's shooting it at this lens. Is that a converging lens or a diverging lens?
Is that a converging?
Mm-hmm.
To be honest with you, that's the last chapter that I had, like the only chapter that I struggled the most with.
All right, so think about it this way.
And
When things converge, do they get closer together or further?
yeah, they meet at a certain point. When they diverge, they separate.
Yeah, so converging, they get closer together. Diverging, they move further apart. So, so what's happening after it hits the lens?
It's converging.
Yes. So yeah, that's a converging lens. Okay, and it hits this sample, right? And basically, what's happening in the sample? It's a sample of some type of molecule, right? And okay, and then so it does something, right? It's going to be at some point or some energy level that will break like a bond, right?
Where does it say that? Or
just where it says it's used to determine the bond dissociation energy, enthalpy.
Of solid molecules, yeah.
Yeah. So essentially, it's gonna break, some type of bond, and the energy, basically, if there's an excess amount, it will hit that energy meter. But before it does that, once it hits that sample, it's also going to transmit the energy into this oscilloscope, which is basically how it measures like sound.
Okay.
But you can't they're gonna explain it after. So the next paragraph says it's a monochromatic pulse laser beam. Is focused on the sample cell using a thin lens. Each photon causes the cleavage of a chemical bond in the solute molecules. because the photon energy is designed to be larger than the energy needed to break the bond, the excess energy is absorbed by the solution, causing a local temperature increase. Okay?
Yeah.
This fast and localized heating process creates a sound wave that reaches the microphone. Oh, I forgot to mention the mic. Yeah, there's the microphone there.
Yeah, I saw it.
And yeah, that sends it to the oscilloscope for recording. The amplitude of the sound signal is proportional to the amount of heat produced. So let me go, whoops, to this. Why is the whiteboard like this? That's so annoying. At the worst possible time. But okay, I just want, all right, it might. Okay, so I would just write, since I can't show you what I'm writing, but I would write, delta H sub NR.
Are you writing something right now?
I was going to, but
Oh, okay.
I'm still having issues with that. So I can write it here.
Yeah, that's fine, because it's, I mean, as long as I can see it on the screen.
Okay. So, all right, here we go. So I'll write delta H sub NR. And so, and that's proportional to basically. Okay, all right, now.
Oh, there it is. I was like, oh, I can't see it. Okay, delta H, okay.
Yeah, okay. So delta H and R, I'll say is proportional to, well, I'll hold off on that for a sec. The energy in the photochemical reaction, delta H sub U, like that is basically, that's basically the bond, dissociation energy. And it's equal to the difference between the laser pulse energy and the heat detected. So here we go. So what essentially is happening is pulsed laser that has a, so if, let's say, the pulsed laser energy was equal to the energy of the bond dissociation.
Mm-hmm.
If that was the case, then there wouldn't be any excess, right?
Yes.
Which means that we wouldn't be able to measure anything in our oscilloscope.
Okay.
So that's why I wrote it's the excess heat, right?
Right.
And so in other words,
H and R, hold on, delta H and R is the amplitude of the sound signal. Oh, sorry. Delta H and R is the heat produced. Okay. Got it.
Yeah, basically, so what I would highlight here is excess energy, right? I mean, like the idea is that, the excess energy get in the solution, which is probably in water, you know, causes a sound wave that is measured as sound. So, you know, excess energy is, you know, that heat produced. So,
Okay.
so in other words, I could say that that the laser energy is equal to the sum of the bond energy and the excess energy.
I can't see where what you're writing. Okay.
Yeah.
Got it.
Yeah, and you know, they then, and you could rearrange that as you wish. And table 1 basically talks about, you know, the bond dissociation energies in enthalpy. So enthalpy is just heat energy. That's, you know, the delta H stuff. So yeah, they have, you know, the different types of bonds and the enthalpy, the bond dissociation energy essentially, and the type of laser that's required. All we know so far is that they say A, B, and C, but you know, in a later question they'll give us like most likely like frequency or wavelength of it, and we're probably gonna have to, you know, find the energy of it and do some stuff with that. But anyway, based on the passage, an experimental feature that distinguishes the PAC technique from the classic calorimetry technique. Do you remember anything about calorimetry?
No.
Okay, so calorimetry basically is like, do you remember maybe doing like experiments where you had like a
Styrofoam cup?
Yes.
Yeah.
So basically with that, it you know, it makes the water temperature increase, and that's how we can figure out the bond dissociation energy.
Yes.
And this does happen exactly the same way in that sample, because it does cause a local temperature increase in the solution. However, we're not measuring the change in the temperature of that solution. We're converting it into sound for some reason.
Okay.
Okay. So yeah. So how is it different from, you know, classic calorimetry? Based on thermometers, they even tell you that part. So yeah. So okay. Let's see. A says, oh, is that PAC? So okay. A says that PAC can be used on samples with specific heats larger than water. I Yeah, I don't see how that.
I have no idea how that is related to the whole pack thing.
Yeah. Because you could just use something else. You could like, if they're not going to use water, you don't have to use water in calorimetry. We base it on water, but you don't have to.
Okay.
So yeah, that doesn't. And by the way, it doesn't say that it doesn't say anything about it being, you know, able to use that. Okay. E says enables the measurement of fast and localized heat transfer processes. Let's leave that there for now. C says is based on the second law of thermodynamics. Well, let's say we don't know what the second law of thermodynamics is.
Thank you. Oh my God. Okay. I thought you were going to ask me, do you know the second law of thermodynamics? I'm like, I'm pretty sure I reviewed that, but not right now.
Yeah, no, everything in the universe obeys the laws of thermodynamics. So, you know,
So it's C. Just kidding. No, let's keep going.
And all right, then D is useful for on samples in the solid phase only. No. No, like that just does.
Why are you saying that? Because of the part that says the solute molecules?
Yeah.
Or no?
Mm-hmm.
Okay.
Yeah. And yeah, so yeah, basically. Yeah, if it was total solid, like, it's gonna be the thing that you want to break apart, and it's not going to cause a local temperature increase in anything else, right?
Right.
Maybe the air, but I mean, you're not going to measure that air. And if it was air, it's not, it says solid phase only. So anyway, B, is the only one that makes sense. So that's a reason to choose it. But we can do better. Because look where it says, causing a local temperature increase. In the paragraph below the figure 1.
Causing a temperature. Okay, yeah. So energy is absorbed by the solution, causing a local temperature increase.
Yep, keep going.
This fast and localized heating process creates a sound wave that reaches the microphone.
Bam.
Is it B?
Yeah, because see, it says.
Oh my God, it's there.
Yep.
Okay, but how about C? Because you said, well, I didn't know that, but you said that basically everything obeys the second law of thermodynamics.
Yep.
So C can be correct as well.
But if everything does it, right? They're asking how.
Oh, so if everything does it, then calorimetry also does it. Got it.
Yeah. Yeah, makes sense.
Oh my God, this is. I don't know if I'm like making sense to it just because you're explaining it, but I hope that whenever I do a question, I actually think.
No, you're making sense of it.
Okay.
All right, let's try the next one. What is the reading of the energy meter in figure 1 when an appropriate laser is used in pack to disassociate a particular chemical bond?
Okay, don't tell me.
Okay.
Hold on. I mean, based on whatever you explained, it would have to be. There's not going to be any energy read if there's no excess heat.
Because the excess heat is going into the, delta HNR.
Right?
Yep.
So it's going to be delta HNR.
Oh, but that's at the oscilloscope. But what about the energy meter?
Well, I don't think it's going to be EM because EM it's equal to delta HU plus delta HNR.
Yeah, and EM is the energy of the laser itself.
Of the actual laser, yeah.
Yeah. Well, so yeah.
You put here that delta HN it's directly proportional to the bond dissociation energy.
Oh, that's my bad handwriting. Sorry. That's a U.
Oh, sorry. Yeah, it's fine. But how did you go? I guess you explained, but how did you actually? Hold on, let me go back to the passage. I guess delta HU.
I think you have the right idea. So what would you say the answer is?
No, I honestly thought it was going to be delta HNR because you said at some point that if there was no excess heat, then there was no energy.
So yeah,
there was no reading on the energy meter, pretty much.
So
that's why I associated that it would be delta HNR.
What did you say before about the energy meter?
that there will be no so like it would reach
Okay.
0 if there was no excess heat.
There you go. Because look, they're asking about the energy meter.
So it's, but you said it was not delta H and R.
But you literally just said the answer.
Okay, hold on. Let me see. If there is no,
because remember,
oh my God, yes.
Yeah.
If there is no excess heat, it's
Well,
actually going to be, oh, okay, no, go ahead.
So what you said was there's going to be no reading on the energy meter, so it would be 0.
Mm-hmm.
And that's what they're asking. They're asking what's the reading of the energy meter.
Oh, but wait. So it's 0?
Yeah.
But how do you know that there is no excess heat how do you know that there's no excess heat?
Because, well, okay, light isn't going to really like carry heat. So what happens is the light adds energy to the bond, causing the bond to break. And in the breaking of the bond, it releases heat energy, right?
Mm-hmm.
That heat energy goes to heat up the solvent, right, in the sample. And all of that, so that causes a local temperature increase. And all of that gets, goes through gets measured by the microphone and is like all that excess heat is basically measured through the microphone oscilloscope.
Okay, I know this might be a dumb question, but how come it doesn't get measured by the energy meter though?
Because, so a good question is, why is the energy meter there? And it's there as a negative control. Because if you do have a reading in the energy meter, it means that your microphone setup is not doing its job.
Why?
Because the object of the entire thing, right? Like photoacoustic, right?
Mm-hmm.
Is basically how that excess energy gets turns into sound.
Okay.
And that's what the microphone picks up, and we measure it using an oscilloscope, which is basically like waves, like sound waves, but like kind of like sine wave.
Right, but so what is the energy meter measuring? Is not measuring energy too, like, because I'm trying to, isn't like heat energy as well?
Yeah. So okay, if you look at, so the highest energy thing here is from the laser. And then some of that energy goes in to break the bond, and the rest of it is the excess heat that's measured by the sound apparatus. So this is like, there's not going to be any extra energy that will reach the energy meter, because if it did, then you're going to have basically, you're not going to be able to figure out the enthalpy, or the bond dissociation energy, which is what you're trying to
So what you're saying is that all the energy from the pulse laser is being used to break the bonds of that solvent?
it's like energy conservation. Like, this is the max amount of energy, and some of it is used to break the bond, right? Like, okay, let's say we didn't have that microphone setup, right? And we shoot a laser with I don't know, a billion energy units, right?
Right.
And of course, the bond is going to break. But how do we know that the bond dissociation energy is like a billion? Because it's just too much. So we need a way to measure how much excess there is in order to figure out the actual bond dissociation energy.
Okay.
So like, yeah, I'm trying to think of like an analogy.
Because that was always very confusing to me, like, because you know how, like, usually it says that whenever you break a bond, that's when you're releasing energy, but in reality it's not really that. It's the difference between if there's any excess energy between the breakage and the formation of that bond. So forming bonds is what actually creates energy. You
um
know how
mhm.
they, I don't know if that's confusing.
Well, it's confusing because there's like bond dissociation energy and there's like whatever. I think like just bond energy itself. But if we're talking about bond dissociation energy, it's just the energy that is required to break the bond, right? So, for instance, like, all right, let's just look at table 1 for a sec. Let's say we have an OH bond, right?
Right.
And or rather, let's say we have a CH bond. All right, and let's say we shoot it with laser that has an energy of 463.
Okay.
Now, if we didn't have a way to measure the excess amount, we wouldn't be able to know that the bond dissociation energy of the CH bond is
It's
463. Yeah.
No, it's 375.
Yeah, but we wouldn't be able to know it, right? If we shot it with something that is higher than 375 and we don't have any way to measure the excess heat, we would never know that it was 375.
Okay, I get that part. Now, where is that excess heat coming from?
It's coming from the laser. The
So
laser,
whatever is not being used turns into heat.
pretty much, yeah.
Okay.
Yeah. So, yeah. So basically, you know, the laser is going to be the thing with the highest energy. It's going to be higher than what's required. And it's that for a reason, because that's how, you know, we measure like, so like let's say this is laser energy is a total energy. And it splits into energy that's used to break the bond and then the energy that is just excess heat.
I get it now.
Yeah. And like, yeah. So you know, some is just, you know, some energy is just always lost as heat, generally speaking. But yeah, but we can measure, like, so we can't measure the bond dissociation energy. Like, we can't really measure that directly.
But we can just subtract it because we know the energy of the laser and we also know
Yep.
the excess heat. So
Exactly.
whatever it's, yeah.
Yep.
Okay, so EM will always be 0 unless, no,
Yep.
unless nothing. I mean, it's always going to be 0, right?
No. EM or energy meter. EM is the laser energy, and that's going to be greater than, you know, either of these. But that's how you can figure out what the bond.
Oh yeah, I'm sorry. Yeah, the reading on the energy meter is not actually EM. I'm sorry. Yeah.
Oh yeah. Now, if we did get an energy meter rating that measure or value that is not 0, that means, like, you know, because this is from, you know, conservation of energy. That means that we're not, you know, doing our job here, because some energy, you know, goes to the energy meter. So you know, if we were able, so I guess then we would have to add energy meter energy to this or something to figure that out.
Yeah.
But yeah, that's what, yeah, I think you get it, because we wouldn't be
I get
that would
it,
figure
and
that
it
out.
makes a lot of sense, but you were the one who came to that conclusion, because I would never, like when we were reading the passage, I never thought that the energy meter was there as a negative control.
Oh yeah, I just added that, but you know you knew that it was 0, like you know.
Okay.
Yeah. Oh, and by the way, it says when an appropriate laser is used.
Right.
If it was not 0, then it's an inappropriate laser. The guy messed up.
Yeah.
All right, make sense?
Yes.
Okay. Oh yeah, another thing, like what if you know, the calorimetry experiments, what if you didn't use a styrofoam cup? What if you used a metal cup? Styrofoam cup works to insulate it, so you're not losing heat. So so all that heat
You're
goes
measuring it with a thermometer, right?
exactly. And now
Yeah.
with PAC, just replace the thermometer with a microphone.
Yes.
Yeah, but if you were using a metal cup, it's gonna be losing. You know. Okay.
Yeah, it's gonna be losing the temperature, or like, yeah, you can read the temperature. I'm thinking of the microphone in this case, like, or not, it can't really act as an insulator, but pretty much if you wouldn't be using the right device to get the excess heat, then you will probably get like a reading on the energy meter. No?
Yeah, like the thing with the microphone is, what makes it special is just that it's fast.
Okay.
So it doesn't need like that sample doesn't need insulation around it, because whatever heat is produced is immediately taken up by the microphone.
Got it.
So
Okay.
yeah. Okay. So let's see. Okay, so the next question, right?
Yeah.
All right, which structure is common to all 3 compounds mentioned in the passage? So I'll look at table 1. So it has to have an OH group. It has to have, wait. Okay. Oh, wait. So, okay. Above that, it says table 1 summarizes the values of, oh, okay. OH bonds in phenols.
SH bonds in thiophenols and CH bonds in alkylbenzenes.
Mm-hmm. So what do they all have in common?
Thiophenols on aromatic ring.
Perfect.
Really? That's it?
Yeah, because a phenol is a benzene with an OH group. Thiophenol, benzene with a SH group.
With an SH, and then
And
alkylbenzene is same thing.
Yeah. Perfect.
No, it can't be that easy. Come on.
Yep.
Okay.
All right. Next one. According to the passage in the data in table I, they mean 1. Okay.
Yeah.
What feature must distinguish laser A from laser C in order to be suitable for cleavage of the bond specified? Okay. Laser A must.
Wait, I know. So laser A requires, or to break an OH bond, you need higher energy, right?
Yes.
Which means that the frequency needs to be higher.
Uh-huh.
Okay, so right now I'm going for B. Let's see if it's C. Have a longer wavelength. That would mean that longer wavelength, less frequency.
And therefore less energy, right?
And therefore less energy. So not C. Emit fewer photons per unit time. I don't know what that means. And then B, better focused laser type C. I don't know what that means.
So yeah, so better focused, like yeah, that doesn't really matter. But they emit fewer photons. I see this type of thing, this type of trick asked a lot. Because so,
that's less energy.
So
No?
that's the thing. So it comes up a lot because it makes people think it's less energy. But the energy of a photon, is dependent on its frequency, and that's inherent in that photon. The amount of photons doesn't change the energy. All it means is there's more photons, aka it's brighter, aka luminosity, aka intensity.
Oh, okay.
Yeah. So I see I see this type of thing a lot. So yeah.
Can you actually, like, I see what you're saying, but because the photons are not related to the energy, I thought they were related to the energy.
They are. So let's say we had a photon that has, the 463 thing needed, right?
The 463. Okay, yeah.
Okay, let's say that we need it to be 463, but it's like, I don't know, like 200. You can shoot like as many photons that have that energy of 200 at it, but it still doesn't mean that it doesn't satisfy the energy requirement, because the energy of a photon is based on its frequency, and if it's just doesn't have enough energy, adding more of that isn't going to help. It's just going to be more weak photons.
Okay.
Yeah, like because like energy of a photon is dependent on its frequency, right? And that's pretty much it. It doesn't matter how many photons.
It doesn't have like an additive effect.
Nope.
Like if I just add like a bunch of photons that are like 200 to make it up to that 400, it's not possible.
Nope, because each time the photon hits that molecule,
It's gonna hit it at an energy of 200.
Yeah, and let's say you need an energy of 463 to cause, or think about it also in terms of, let's say if it was just an atom, right? And for it to get from like from its ground state to its excited state. So that's why it's called quantum mechanics, because everything is a is a discrete
value.
Yeah. So like, if you need a specific amount and you don't have it, it's not going to do a single thing.
Right. So it's not like it's going to do half of the work. It's either going to stay it's like an all or nothing thing, basically.
Yeah, exactly. So it doesn't matter how many, you shoot at it, it's still not going to be enough if it's not the right type of photon.
Okay.
Make sense?
Yep.
Okay. All right. And then the one after, yeah.
I mean, it's B, right?
Yeah. I mean, I'm pretty sure, like, but yeah.
Because I'm not. So all this time I haven't been clicking on the answers.
Oh yeah, I'm just just going through it. But I don't have answers like in front of me, but I'm pretty sure.
Okay.
Like 100%. Okay.
Okay. 100% is enough for me.
Yeah. Okay. Now let's see. Based on the ray diagram, the distance is shown, the focal point of the lens. All right. So this is where I will share this math thing with you. I'm sure you've seen like this before where, wait, not that math thing. Whatever, some math thing here. Where, okay, it's not there either, but if you have any type of
you showed it to me yesterday, but I guess you told me you were gonna send me something, but I guess we forgot about that part because you told me like if there's something that you need to memorize, it has to be that.
Here. Oh, yeah. No, this is what I was talking about. So any type of reciprocal summation, like let's say okay, what would this be? When is this
That's
used?
resistance in for parallel resistors.
Okay, and this is capacitance, right?
Yeah.
And then this is,
Oh, that.
like focal point and object and distance and things like that. So
Okay.
do you know, so you can just rearrange this as the product over the sum.
Yeah, so I am familiar with the two, with resistance and capacitance, but like I said, like everything that pertains to lenses, I really consciously avoid it just because I think it's extremely complicated.
Oh, okay.
So I see that formula. I believe that formula pertains to lens, right? Yeah.
Oh, yeah. So yeah, I was just saying like any type, like instead of using
Oh, yeah. Oh, like if I had two fractions and I'm adding them, I know how to get from that. So basically I just do a basket shape type of thing. Is that correct?
I don't know about
That's how they tell me. So basically, if I have two fractions that are adding, what I would do is I multiply and cross. So that's why it would. Oh wait, what? Yeah. Okay, it's a reciprocal. So I would go ahead and do. Is that an L? Is that a letter L or what is that letter?
Oh, this is an I.
And then the one on the top, is that an L?
Oh, sorry. Yeah, these are all ones.
Oh, one. Okay.
Yeah, that's why I was saying for any reciprocal like sum. Yeah, it would be the product over the sum.
Got it. I get that part. Yeah.
Okay.
I thought you were talking about the formula, and I was like, I don't know that formula.
Oh, yeah. Okay, so yeah. Basically, yeah. Think about it like well, let's see. So, okay, if you look at that figure 1, right? The distance from the pulsed laser to the lens, right?
Yeah.
Is going to be one thing. The distance from the lens to the sample is going to be another thing.
Yeah.
And then whatever, focal point or focal length rather, that's what we have to figure out. So okay, and then O stands for object distance, I stands for image distance. So we have 12, like the 12 centimeter one and the 4 centimeter one. So which do you think is which?
So O stands for object distance. So object distance is going to be 4.
You know what? I just realized it doesn't even matter because it would give you the same answer. It would give you the same answer regardless, right? Because
even before that, and probably I am biased by the fact that I don't know this formula, but how would you know that you have to use that formula though? Or is this something that I need to know?
I would say, yeah, I would say you need to know it. Yeah.
Yeah.
That's like the thin lens equation. So yeah, I would say
Okay.
yeah.
Short answer, yeah. All right.
You know it. But yeah, it actually doesn't matter which one is the object length and which one is the image length because the product and the sum will always be the same.
Oh, wait. So, for example, if it's 12 times 4, that's going to be 48, and then 12 plus 4, that's going to be 18. Oh, it's always going to be. Yeah, it doesn't matter because you're always going to get the same. Got it. Okay.
Yep. So, okay. So we'll just do that. So yeah, 12 times 4, 48. 12 plus 4, 16. 16. Wait, what am I talking about? 12 times 4 is, 48.
48.
Okay.
Yeah.
Over 16.
That's 24. Half
4
is
goes into
4.
12.
12. That's 3. It's
Yeah.
8.
Yeah.
Okay.
So yeah, that's basically the focal length of of the lens.
Okay.
Yeah, there's like on Reddit I wrote like this optics guide, which you can also take a look at. I can send you the link, but yeah, this is a good good one to remember. Like, yeah. Okay. So, all right. Okay, so here is where I would. So, okay, the next one, 12, the kinetic energy of something produced in the energy meter when the frequency of the incident photon that is not absorbed in the solution is. So they give us the frequency and they give us Planck's constant in electron volts.
Oh, okay.
And so something. Oh, that was me like starting to draw like this bomb calorimeter thing, but okay. So there's something called. Have you ever heard of a work function?
A work function, most likely, but I don't know what it is. I mean, can you show me?
Yeah.
What?
So okay. So all right. So here's kind of an example of a photon. I don't know why I wrote like that's not really a V. It's the Greek letter nu, which looks like a V, which means
Okay.
frequency. But I should have just wrote HF. But yeah, let's say a photon hits it, right? And it causes, it to get to an excited state. And then when it goes back to the ground state, it emits a photon with equivalent energy, right? Okay, now let's talk about things like if the photon energy was greater than that was needed to cause it to get excited,
Yeah.
the electron will no longer just be at this excited state. It's going to be like no longer attached to the atom, but more than that, the excess energy is going to cause the electron to shoot out.
Okay.
Yeah. So if you were to, and so the work function is this over here. I forgot what's like Greek symbol that was. Maybe like, I don't know, phi or something. I don't know. But that represents the work function, which is basically, in other words, like kind of like the ionization energy. The energy required for it to no longer be attached to the atom.
Okay.
And
But
therefore,
but
yeah.
what do you mean by like work function? Like what is that? Is that
Oh yeah, so it's just just like whatever, a fancy name for it. But think about, okay, so ionization energy, right? It's the energy that's required to cause something to become an ion, right?
right?
So, let's say it becomes, whatever, a positively charged ion or something. That means that the electron is given enough energy to no longer be bound to the atom.
Right.
So that amount of energy is the work function.
Right. But then that electron doesn't become a positive charge, does it?
Oh no. I'm just saying,
that was another example. Okay.
for the atom or whatever.
Okay.
But yeah, for that's why, ionization energy causes the atom to ionize.
Oh, wait.
Yep.
Oh my God. So what happens when you call it ionization energy is that it I mean, this is stupid, like I already knew this, but it emits the electron because it has enough energy for the electron to kind of detach from the atom, and that's when the atom gets the positive charge.
Yeah. But yeah, that's just, the atom. But
Okay.
yeah, it's just enough for it to detach though. But if it's more than that, that excess energy goes towards kinetic energy and pushing that electron out with some velocity.
Okay.
So if it was equal to the work function, right, it's just going to ionize the atom, which means that the electron is no longer going to be bound. Anything more than that, and it's going to go towards, getting it to move.
Well, if the atom is ionizing, wouldn't the electron already be moving because it's detaching?
So it'll detach,
But it won't move.
Yeah, unless it's greater than the ionization energy, and it's the same kind of
thing. So if
thing.
it detaches, where does it go if it detaches?
I don't know. It just whatever. It's like they broke up, but they still live in the same apartment. I don't know.
Okay.
But basically, like, yeah, all it tells you is that it's detached, right?
Mm-hmm.
But it's not gonna, like, it can't move on its own. So yeah, so if it happens to be that photon that you add is greater than that ionization energy, that energy is going to go towards making it go faster.
Okay.
Or sorry, to make it move.
Yeah. Got it.
So yeah, so basically it's kind of like the conservation of energy with enthalpy, but it's conservation of energy but not with heat energy. But rather
it's with kinetic energy.
Yeah. So like think of this, the work function, aka ionization energy, as being analogous to the bond dissociation energy. And then this is like, the excess, and it produces, this type of thing. I shouldn't say, no, it's more like this is the excess, sorry. Where
Okay.
this is the highest amount. Like this thing is the highest out of these two. So here, if I just wrote HF and added the work function on both sides, it would look like this, where that's that. So like this is like the energy of the photon, and it's equal to the energy of.
This is the energy of the photon, which is HF.
Yeah. Yeah, so that would be the greatest thing, so it would look kind of like this. But yeah, so that's the work function thing, and that's something that you should know because they ask this type of thing a lot. They ask a lot of questions about photons and things like that, so so yeah.
Okay.
So all right, so we have the work function, which is 3.4 electron volts.
3.4.
Yeah, it's at the end of the second paragraph.
Okay, got it. The energy meter based on photoelectric effect uses a detector with a work function of 3.4. Okay.
Yeah. And okay, and then we have HF, and so we just use this formula right here.
So sorry, HF will be multiplying those two values on the question.
Yeah. And so basically, if we're going to multiply these, what's going to happen to the exponents?
Let me feel that. Oh, they're going to cancel.
Good. So it's just going to basically be
4.1 times 5.
Yeah, like 20 basically, right?
Yeah, pretty much.
And then we subtract that, but from by the work function, which is 3.4. So basically, we're gonna get like 17.
Oh my God. Yeah.
Yep.
I mean, I got scared by a bunch of like, every time I see a unit that is not the original one per se, like for example, like if I see something in millivolts or I see something in like another unit that requires like scientific notation, I kind of already assume that I have to first convert to the original
Oh yeah.
unit and then work with that.
Yeah. But so far we haven't had to do that because we like remember the one where we had like milliseconds and milliwatts,
Yeah.
and the answer was in micro.
Mm-hmm.
So yeah, you can kind of like be able to see how we don't have to do all like those extra steps and stuff.
Got it. Okay.
Okay. The next one is which alcohol will undergo substitution by an SN1 mechanism in acidic conditions. So I don't really remember any of the orgo stuff, but let's just look at what is the same and what's different. I mean, I remember something that is going to help me kind of figure it out, but like just tell me how each choice is different.
They're basically tertiary, secondary, primary alcohols.
Oh yeah.
But then that's between A, B, C, but then C is actually, well, no. So C and A are both primary alcohols.
Yep. So who cares about those guys?
Okay, so it's between B and C and B and D.
Mm-hmm.
But why do you say who cares? Because they're the same answer pretty much?
Yeah. Because SN1, SN2, like E1, E2, like they depend on, so like even though I said like I don't like remember a lot, so like the major difference between SN2 and SN1, right, is that it is what do you think?
It's the number of steps. So
yeah, so yeah, so if it's SN2, which is like one step, right?
Which I don't know why it's called SN2. It should be SN1 one step, SN2 two steps, but whatever.
I mean, I can go into why at a later point.
No, thank you.
You don't need to, yeah. But okay. Yes. So basically okay, SN2, right? It happens in one step because there is room for it to happen in one step.
That's
right?
True.
Whereas SN1 happens in two steps.
Because you need to make up the room for it to happen, no? Which is the extra step?
Kind of. It's more like it loses like its leaving group, right? And it has that, it turns into like a carbocation. And that is not going to be stable like if it's primary. The more substituted it is, the more that
stable,
more stable it'll be. So generally speaking, like SN1 will be like thing that is more tertiary. So that's why basically the only difference is, and like also like the reason I said forget A and C, because from what they don't really give us much information. So all we have is primary alcohol, secondary alcohol, another primary alcohol, and then tertiary alcohol. Unless you think it depends on the number of carbons, I suppose. But even that wouldn't work because A and B have the same number of carbons, and C and D have the same number of carbons. So it can't be the number of carbons, and it can't be, so it must be, whether it's primary, secondary, or tertiary. And it's definitely not going to be primary because A and C are both primary. So is it going to be secondary or tertiary?
It's going to be whatever is more stable, so tertiary.
Yeah. But if you didn't know that, I would say that if it's not going to be primary and secondary is in the middle and tertiary is the furthest from primary, it's not going to be primary. It's going to then be the furthest thing from it.
Well, but how do you know that? Because it can be the thing in between.
So if it was a thing in between, right, then it should be just as likely to work if it's primary or tertiary, right?
That's true.
But we know for a fact that it won't be primary.
Yep.
So
we know that's for sure that it's not going to be primary.
Yeah.
So the chances are higher that it will be tertiary.
Yeah.
Okay.
So what do you think the answer would be?
So it's going to be D.
Yep.
Okay.
Okay.
Wow. Oh, it's 5:15. I don't know. Yeah, we're over the time.
Yeah. Okay. What do you want to do?
No, I'll stop here as much as I want to continue.
Uh-huh. Okay. So, yeah. So any questions about what we have done so far?
No, not at all. Well, if you can actually send me the recording.
Oh yeah. Yeah. Okay.
Whenever you have a chance, it's fine.
Yeah, I can send that. Okay. And let's just see what so like for the next time we and also like I'll add things to the notebook that I wasn't able to add.
Oh yeah. So what do you? Yeah, I guess it's also my email though. Like I don't know. Maybe it was probably my fault. I guess we will arrange like to make sure it works for next time.
Oh yeah. So try getting the program on your laptop and then opening it in the notebook.
Okay.
Because yeah, it's always better to use like the program because it doesn't have to go through like your web browser to update, and also you just have a lot more like options, like because that's why my thing was updating like faster.
Is that the actual app on your desktop?
Yeah, you see,
Okay.
because you see how different it is and how much more options I have.
Right. But like that's what I was trying to do in the app on my iPad because I have the Zoom meeting on my
Oh, I know what I
laptop.
did. Sorry, I know what I did when I was trying to log into whatever the Microsoft thing and it wasn't working. I changed my password.
Oh.
That's why it wasn't syncing properly. So yeah, I can fix that, and I can add more better explanations of things.
Okay, but
yeah.
I mean everything that you've covered so far has been like really clear to me. So
All right, that's good. I just want to let's see. So for next time, so what are you going to basically for before next time, like do you want to do some problems from here and we'll go over them?
yeah, I'll definitely do that. Especially I want to put more time into the chem physics section. So yeah, I'll do that, and then whenever I have like a good amount of problems done, then we can go over those if that sounds like ideal for you. I don't know.
Okay, we could do that, and yeah, I'm just looking through these, and I'm trying to think if I should tell you to do like any specific one.
Oh, got it. Okay.
Let's see. okay, like let's say that just for, like what generalized topics, I'm sure like your UWorld tells you like which kind of topics in CP that you have like the
Yeah,
most.
and I know exactly like what is harder for me to do in physics, especially like everything that has to do with energy and hold on, give me a second.
Yeah.
With waves and sound light, like all of that stuff and lenses, like magnetic fields and all
Mhm.
of that. It's like it's
Yeah.
challenging for me. Yeah, it's confusing more than challenging. It's like
Yeah. Okay. I have, I'll add some content for that because I'm pretty sure I talked about it somewhere here. But yeah, I'll add some of that stuff. Oh, you know what? This is like right after. Okay. Right, like the problem that comes right after the one that we just did. Um,
oh, okay.
okay, so okay, energy, like like magnetic waves and things like that.
Yeah, if I go to UWorld, let me see something. Hold on.
Okay.
UWorld really quick. So UWorld has light and sound. They have 47 questions for that.
Here, let me let you share your screen.
Oh, okay.
Okay, go for it.
Okay, so how do I actually? Okay, here. Can you see it?
Mm-hmm.
Okay, so yeah, what I was telling you yesterday, like it breaks it down in different sections.
Yeah. What do you get when you hit performance?
This one,
Yeah.
it shows you all the breakdown of all the questions you've
Yep.
done.
Yeah, that's what I want to see. So, like, go to like reports perhaps. I just want to see, some more data. Okay, perfect. So, like, it's so basically, yeah, your behavioral sciences are good. So, okay, if you like click on the plus sign next to like Gen Chem and physics, it'll show me like which topics in those areas, right?
Oh, because
Electrostatic.
the only thing that I've done for physics is because I was covering by unit. So the only thing that I've done of questions for physics is electrostatics and circuits.
Oh, okay. All right. What about general chemistry?
Just atoms. And so this like pretty much Gen Chem and physics is the least that I've done just because
Oh, I see what you're saying.
yeah.
Okay. Okay.
Yeah, this is cars. Well, cars, I'm done with it. And then I still have a lot to go on psych, but I've been able to do the most in that section.
Yeah, that's gonna be just pretty much content.
Yeah.
What can you see graphs? I'm curious.
I don't know how that works.
Well, you did different kinds of things, I guess. Like you didn't do like an even spread of like all the topics, so it's gonna not really give you.
Oh, got it. Well, there is also this thing that you go like previous test and it gives you like individual scores like of every section you take,
Mm-hmm.
like every single block pretty much
Mm-hmm.
that you take. So, but I don't know if you want me to go back to the reports.
Oh no. Yeah, I want to see like, get an idea for which types of like which topics yeah, like which topics to like focus on that I can write about in your notebook basically.
Oh, got it. Yeah, so this is the thing, like I've been pushing like or I don't like to encounter questions that I know in the back of my head that I haven't really encountered the content for. So
Mm-hmm.
that's why I've been pushing. And even though like I was done with content in physics, but I'm like I'm just gonna be honest. I'm avoiding it because I don't want to know that I suck. Even though like I review the whole content and knowing that I'm not gonna do well, it's like, what else do I need to do if I already did the content, you know?
Oh yeah, but yeah, you did really well like today when we were going over everything, and you know, we went over kind of pretty much like a question from every single possible angle. So like, you know, that lets you basically, yeah, you did. I don't think that you don't know. You know, it like, first of all, you knew the equation for, you know, whatever, but I showed you like, you know, so I mean, so far the only thing that we seem to needed to know was oh, like that thin lens formula.
Yeah.
Yeah, that's the only thing. But so far everything, you know, you were able to like, you know, figure out. And see, like the thing is, like with going over each of the choices, you learn things in that process. Like for instance, like that question that was like how do you make DHB?
Oh yeah.
We figured out, well, we figured it out without knowing, using logic, and then we learned, you know, what carboxylation was, what hydroxylation was, what reduction was, right? We learned you know, like hydrolysis and dehydration synthesis. We learned about, you know, conservation of energy when it comes to like, you know, something that's not in the calorimeter. And, you know, I related it to your experience, which you said yourself, like with the foam cup. And that aromatic ring thing you got just from, you know, like the passage. You saw, you know, how they all had phenols and benzenes, right? And yeah, you every time I asked you like a question, you were able to get it. And then just anything that was excess, like let's say like, you know, the bond dissociation energy is what you need to answer the question, and then the excess energy is like me just telling you like just some extra information about like fewer photons doesn't really mean anything besides, you know, luminosity or something like that. Yeah. Oh, and then, you know, just, and then with that focal point thing, like just how it doesn't matter if you know which is object distance or the image distance, because you're going to get the same answer no matter what. And then, yeah, you saw like how easy it was to do that HF like calculation by just canceling those out. And you did that also with, you know, the milli things, and then, you know, how that would make micro. And SN1 thing, we were able to, you know, figure out. So yeah, sir. I mean, you know, whatever content gaps you have. So like, this is like the best way of going about it. You answer the questions. You try to figure out why your answer is right and the other answers are wrong, and you learn content. Like that's the gap. Like a gap, like shouldn't be like this, like a chapter in a book. A gap will just be like, you know, now we know what hydroxylation is, right? Yeah. So yeah, for the rest of the problems, like, you know, of course it's going to be a little bit more complicated, or rather, you know, there's going to be all sorts of stuff. I mean, you know, it's not particularly easy, but yeah, what, like, how much do you think, for instance, there's a question here that's just really too hard, because it's hard alone for physics students. It's this thing called a Wheatstone bridge. Yeah, that's, you're gonna see that. But so okay.
Do you want me to like do your world questions, or more, or to focus more on like to keep working on those question pack?
Oh, because the thing with UWorld is like it's too specific, like if you just do physics or if you just do chemistry and stuff. And so I think, yeah, the best thing is to use, the section banks, because it's just, on a need to know kind of thing, whereas you don't need to know everything that would be in like a UWorld physics thing, right?
Right.
So okay, so how about this? I will like select questions from this section bank and passages for you to do before we meet next.
Okay.
And yeah, and I'll take a look at it now, and then I'll email you with
Got it.
with which ones to do. Okay.
Okay. Okay.
All right. So
Sounds good.
any other questions?
No. How do I send you the money? Can I have a Venmo or like a Cash App or?
Yeah. You could use Venmo. I think
Okay.
my Venmo is just like like Khalid 16. Let's see.
Let me actually open the app.
Yeah, it's I'll put it in the chat. Sorry.
Oh, okay, got it.
So you're gonna come across like really complicated looking passages, and just remember to take it one question at a time.
Okay.
All right. Yeah, you don't have to read it like because
I don't know if that's okay. So you have a picture.
oh, it's not me.
Huh?
It's not a picture of me, but yeah.
Okay, got it. I was like, I don't want to send it to the wrong person.
Yeah.
Okay, let me know if you got it. Oh, I need to include something, I guess.
You know what sigmoidal means, right?
Sigmoidal? Is that like a shape of a graph?
Mm-hmm.
Yeah, is that like the sine and cosine function? No, forget it. It's asking me for the last 4 digits of your phone number.
Oh, okay. 5994.
5994. Okay.
Yeah, sigmoidal is just it's an S-shaped curve.
Okay.
Like that you see in like titration and stuff like that.
Okay. It's not letting me do it for some reason.
Let me see. Okay, how about all right, I'll find you. Oh wait, okay, you did. Wait, how can I find you?
I'll send you my. I'm not very familiar with Venmo, but.
All right, I'll try your phone number, which you sent me in your email. 78
6315 7. Oh, but I send you on the chat my Venmo username or whatever that is.
Oh, okay.
Oh yeah, sorry. I didn't tell you. I sent it to you and I assumed that you were seeing the chat.
Oh yeah, it's okay. So let's see. Is it Buitrago? How do you pronounce your last name?
Buitrago.
Buitrago, okay. Is that like Cuban?
No, I'm Colombian.
Oh, okay. What's that? Oh wait.
I can also do Zelle.
I forgot the E after. Got you. Yeah, hold on.
Huh?
Oh, sorry, not you. Yeah, I'll just do for like 2 hours.
Okay. It should show my on my notifications, right? Okay, got it. Yeah, it says transaction declined. Please try again in a short while. Apologies for the inconvenience. Like, and I'm pretty sure it's like, I don't know. I can try Zelle if you want. Do you have Zelle?
Yeah, okay, we can do that.
Is it with your phone number or your email?
So for some reason, Zelle never works unless I send a request.
Okay.
I don't know why. Like people try to send me something and it says that they tried to send me, but then it says to sign up for it. But it only works when I do by request. So here, yours is by.
I feel like we're having trouble with everything today.
Oh yeah. I mean, better sooner than later, right?
Yeah.
All right. I guess are you in Zelle by?
I
Number?
am with my phone number. So 786-315-7483.
Okay.
Did you request it already?
Yeah, I sent the request.
Okay, got it. Okay. You should have it now in your account.
Okay. Okay. So,
all right.
Yeah. Yep, I got it. So, okay, I'll send you I'll update the notebook and I'll send you like which particular questions to do and passages to do.
Okay.
So, and yeah. And
thank you so much.
Yeah, no problem. And yeah, we can meet again like whenever you want, like.
Okay. This has been the most entertaining physics lecture I've had in the of my history as a student, period. Like
Thank you.
Yeah. Yeah, because when you understand things and when when you actually think of the possibility of getting a question right or understanding something, it becomes more enjoyable. When you see it as like super far away, like this is stuff that I have no idea about, it's a little bit discouraging. And I think that a lot of people are good at making things complicated, and that's the problem why people don't like physics.
Yeah. Like yeah, I can. So yeah, I'll try to like explain things in a conceptual way that would make, because like for instance, when I see like an equation, I always ask like why, right? Like why is, when you add resistors in parallel, is it a reciprocal sum, which means that the resistance goes down, right? And
Right.
also, like, why is that the case for capacitors?
Capacitors in series, yeah,
I mean,
that's true.
just for any capacitor, they don't have to be in series or not in series. Like when I say that, I mean capacitance. Um, and it's for the same reason that it's the same thing with resistors in parallel, because as the area of the capacitor increases, basically they're able. Well, whatever. I'll talk about this.
Okay. All right.
Yeah.
Got it.
All right. Take care, though.
Thank you. So I'll keep an eye on the email too for the exercises, and then I guess we'll keep contact as to like to make sure that the notebook works.
Yeah.
But I'm gonna download the app on my computer.
Okay.
Okay. Thank you.
All right. No problem.
All right. Bye.
Yeah. Good luck.